The function f of k is defined for positive integers by f of 1 equals 1, f of 2 equals 1, f of 3 equals negative 1, and by the identities f of 2k equals f of k, and f of 2k plus 1 equals f of k, for k greater than or equal to 2. The sum f1 plus f2 all the way up to f100 equals negative 15, 28, 64, or 81. Okay, so the first thing to see here is that all of the values of f are going to be either 1 or negative 1. Given the initial values that are all 1 or negative 1, and we see that future values are defined only in terms of initial values, not even by doing operations on any of the other previous values of the function. So I think what I want to figure out here is, of course, for which values of k is f of k 1 or negative 1. And then, I think there's going to be something, perhaps something to do with powers of 2. All of the powers of 2, for all the powers of 2, f of k is going to be equal to 1. Right? We see that f of 2 equals 1, and f of 2k is equal to f of k. So every time I multiply this by 2, going from here to here, the value of the function stays the same. Can we also say that for odd values of k, it's always equal to negative 1? Why don't I don't want to just completely start making a table of values here and try and decipher the pattern. I want to kind of try to figure out what the exactly which numbers will give 1 or negative 1. So it's not true that odd values of k always have negative 1. For example, f of 5 is equal to f of 2 times 2 plus 1. Let me write down the other identity that we're given. So f of 5 is going to be equal to f of 2, which is 1. Well, the only way we're going to get a negative 1 is if the function, in building backwards through these recursions, we end up at f of 3. I always end up resorting to just writing a table of values for these types of questions, which, I wish I could just figure out what the pattern is based on the relationship given itself, rather than brute forcing and identifying visually what the pattern is. But here we are. Okay, so the idea here, once we have these first two, we have 2 1s, 2 negative 1s, 4 1s, 4 negative 1s, 8 1s, and I suspect we'll have 8 negative 1s. Yeah, because 26, 27, 28, 29, 30, and 31 are all going to give -1. So if I write out if I'm taking things, and of course, these in the sum, those 8 are going to cancel those 8. So f of 1 plus f of 2 plus and so on up to f of 100. F of 1 is 1. A huge number of these are going to cancel out. Right? F of 2 cancels f of 3. But we need to figure out where this pattern there's going to be leftover numbers here where the pattern hasn't quite finished yet. So the answer is definitely not -15. It's going to be a positive number. It's probably 28. So 32 up to, well, we have 8 in a row here. There's going to be 16 in a row. So 32 plus 16 is 48. This will go to 47. And then 48 up to, if I add 16 to 48, that gives me 64, so 63. These are all going to cancel. And so then we have from 64, there should be 32 values of 1. So that'll take us to 96, 95. And then we have 96 up to 100 will be negative. So that's 32 values that are equal to 1. This is 5 values equal to -1. So the answer should be 1 plus 32 minus 5, which is 28. Yeah. I mean, this wasn't terribly difficult. I just sort of made it more difficult on myself by trying to not do this. I was hoping to just be able to see the pattern for myself, or figure out what, derive what the pattern of ones and -1s is based only on the recursion that is given. Once you start creating this table of values, it becomes pretty obvious. But I was hoping to see that without going through all the computations. Anyway, not too bad in the end, but if I have more to say, I'll put it in the description. Thanks for watching.